So welcome to the 32nd quarterly meeting of the Northeast Digestion Roundtable hosted by NEBRA. We've been doing this since 2016, and we've been sponsoring these sessions to exchange information and share best practices for anaerobic digestion. It's an informal meeting. We'll have a formal presentation, but it's informal. You can ask questions, take yourself off your mic later, put your camera on, ask questions. We're going to definitely have time for questions, and you could, if you want to, type them into the chat. That would be appreciated, just so we can see them in advance, but not required. I am recording this. We'll share this, post it on the website, and get you a recording link next week. I want to start out by giving a big shout out to our sponsor today, BDP Industries. They are providers of custom thickening, dewatering, and composting solutions for our industry. And actually, they supplied the belt filter presses for this project here. And without further ado, I'm going to introduce our speaker today, Matt Van Horne. He is an associate vice president with Hazen and Sawyer in their Fairfax, Virginia office. He's been there for 16 years out of his 22-year career. He's registered PE in 8 states. He's completed his associate DBIA certification. He has bachelor's and master's in civil and environmental engineering from the Massachusetts Institute of Technology. His main focuses are biosolids management, energy optimization, and wastewater treatment there at Hazen. So I'm going to ask Matt to go ahead and take over the screen sharing and stop.
Sounds good. Can everyone hear me and see my screen okay, hopefully? All right. Just clearing a couple things out of the way here. So I lost my other screen. Okay. Janine, you guys can hear me okay?
Yeah, I can hear you.
Okay, thank you. Just wanted to make sure everyone could hear me before I get started. All right, so today we are going to talk through a little bit about the WSSC Water Bioenergy Project. So we're going to kind of talk about from plans to production, and what we see here is the picture on the screen is our design 3D rendering, and from the design 3D models. And what we'll see is this, as we look at the actual picture, this is from a few months back, but right towards the end of construction. I think the team did a pretty good job at turning a 3D model into an actual facility. So we'll talk through some of that as we go through today and kind of hit on some of the highlights of what we got going on here with the project. So what we'll talk about today, a little bit of background of the project for those who don't know too much about it. Hit on a couple of the key digester-focused design decisions. Certainly a lot of other aspects to this project beyond just the digesters, but this being the Digestion Roundtable, we're going to focus on that part for today. And then get into some of the little update on construction and talk about commissioning, because that's kind of where we're at currently, and I think some interesting lessons learned and topics from that item. So talking a little bit about the background of the project. So first of all, this project was delivered as a design build project, and I can talk all day about the technical parts of this work, but I think it's really important to acknowledge all the people that were involved. And that's really what made the project successful overall. So Hazen was part of the design build team with PC Construction and Stantec, and then a lot of involvement from HDR and Brown and Caldwell, kind of also as the program management team. And certainly WSSC played a big role throughout. And it really, again, it's really the individual people and just their commitment to the success in the project that really made this one stand out and made it really a lot of fun to work on. So we will, we'll go with that. And then you see a lot of relatively prominent engineering logos here. So you can imagine what some of these design workshops look like, and what then kind of the very interesting conversations and opinions about what different design elements should be. So there's a lot of influence buried into each of the different components we'll talk about today. As we talk a little about the overall context for the project. So WSSC, they serve water and wastewater to the 2 counties in Maryland, just on the north and east sides of Washington, D.C., Montgomery and Prince George's County. This project is going to centralize their biosolids processing at the Piscataway treatment facility, all the way down here at the bottom. This is a little bit of an older graphic. These are now all water resource recovery facilities, so no more WWTP, where they have taken the step into the resource recovery field. But so trucking solids from these other 4 facilities all the way down to the southern part of Prince George's County. And for those who have ever driven around DC and around the Beltway, this is going to pose a very interesting challenge, I think, as we get into different traffic conditions and weather conditions through this area. So that is the plan for this project, and that's kind of how they're getting all the solids down here to the south. As we look at the goals of the project, really, it's these 4 things here: make Class A biosolids, reduce operating costs, produce an RNG product that they can then sell back to the grid and obtain some RIN credits, and also overall reduce their greenhouse gas emissions. So these are the things that kind of drove the project. This project has roots going back into the late 2000s, early 2010 timeframe through some master planning, and then moving into more conceptual development. And then the design build process really started in about 2018 as the design kicked off, and we moved forward from there. So on the design and construction side, really haven't been at it too long. It's been 6 years, 6 years to design and construct the project. It's about a $271 million design build project, and we'll start getting into what some of the specific pieces are. So as we look at kind of a very simplified flow schematic for the process, so we'll take a second here so everyone can understand where we're coming from. At the Piscataway site, the Piscataway solids, they will go through gravity thickening, solid screening, and pre-dewatering. All the other four facilities will have their solids screened and dewatered offsite, and then trucked from there to Piscataway, and they'll all combine together in these cake bins. From those cake bins, they'll pump through the thermal hydrolysis process into digestion. The solids will continue on to post-dewatering, where it'll make its Class A cake. The digester gas gets cleaned up and sold back to Washington Gas, the local gas utility's renewable natural gas. And the filtrate from post-dewatering goes on to a side stream treatment process before it's returned to the Piscataway facility. One of the interesting things is that the Piscataway facility is about a 30 MGD design capacity facility that is now dealing with the filtrate in the side stream from almost 90 MGD worth of wastewater processing capacity. So you can imagine the importance of this side stream treatment process was really critical to the project's success. I could do another full hour or more on the side stream process, but we won't go too far into it today. Certainly happy to answer questions about it, but we're going to, again, stay focused on digestion for today. Be a little bit on side stream, but again, focus on digestion. So this is kind of to put some numbers to it in terms of a mass balance. This is what was the design 2040 average annual mass balance condition. You can see kind of our total input to the facility was projected to be about 72 dry tons per day. As we look at losses and stuff through the process, we're getting about 68 or so dry tons per day into the bioenergy facility on an average basis. The design maximum throughput is about 92 dry tons per day. What's interesting is that even as we sit here today, we're processing in 2025, we're processing 65 to 70 dry tons per day already. So clearly we're seeing some a little bit more solids than what we anticipated. But the nice thing is the facility has the capacity to handle some extra. So this isn't a huge issue. And most of these facilities are pretty close to build out conditions also. So there's not a ton of future growth of solids production in these areas. Talking a little bit about the benefits here, and these kind of going back to a little higher level. So WSSC for a long time has had a lot of lime stabilization used for their biosolids, making a Class B product for land application, some in Pennsylvania, some in Virginia. This is really designed to fundamentally change how they look at biosolids. They're really trying to take that next step and making them into a more valuable product. And then as we look long-term, even beyond just this Class A cake they're producing today, starts to give them more opportunities to develop this into different markets, looking at different future ways to augment or treat some of this material, create different products, and really try and diversify their biosolids portfolio. All of this together, really trying to look at how can they optimize their operational costs and really be more efficient for their ratepayers. But all these benefits aren't free, and we know that. So we talked a little bit more about the nitrogen recycle and all that gets returned to Piscataway. That's a very much a non-insignificant component here. So we need to make sure that what we're sending back isn't going to impact the ability of the Piscataway liquid treatment facility to meet their discharge permits. And again, talk about that side stream, and that is a critical element, and that needs to achieve 85% ammonia removal before it goes back to the liquid stream. So really pushing that as much as we can to not impact the Piscataway facility. One of the big challenges that we have been dealing with for the last almost year now is this concurrent startup of digestion plus the side stream treatment, dealing with multiple biological populations, each with different drivers and different comfort zones, and trying to do that in a way that not only has them started up well, but also started up in coordination and trying to balance that with the realities of trying to get these other facilities all with their solids sent here to Piscataway. So it's been, we will spend a fair amount of time towards the end of this talking about the commissioning and how we kind of work through that. So we'll come back to that piece in a little bit. But we talk about benefits and talk about challenges, but we got to have a little bit of fun. So at the ribbon cutting for the facility, so I had never before seen a 15-foot inflatable toilet. That was new for me. And the RNG that they're producing from here is actually kind of intended to fuel a fleet of buses for Prince George's County, and so they had one of the natural gas buses there with its poop to power sign there, and it's on its front end there. So that's kind of one of the WSSC has really embraced this poop to power concept. They're using that in a lot of their public outreach materials. You can go look at WSSC's website, just search for WSSC Bioenergy. They have a whole website on this, a lot of information. There's been tons of news stories written about it. And actually, for those who might be attending the Biosolids conference in Baltimore in May, there's a whole the Tuesday workshop, a half day in a classroom, and then a half day tour. I have no idea if it's sold out or not, but certainly happy to give a tour to anyone. And Oleg, I saw you here on the call a second ago. He was the recipient of a tour earlier this week, so hopefully he can attest that it was a little bit rainy, but hopefully it was a good trip for him. So
great trip. Thank you so much.
You're welcome. All right, so let's get into the design decisions a little bit and talking about kind of how we got to where we are. One of the big challenges we had was that we look at this rendering, it's like, oh, there's a lot of green. We must have a ton of space. Not really. So the reality is that this is a very optimistic site rendering. Obviously doesn't show a lot of any underground utilities. As we look at it from a little different angle and from an actual picture, you can see where we are. This is kind of looking again, before we were looking from the right to the left, but as we look kind of from this direction, we can see on the right side, all of the liquid treatment processes butting right up here to the bioenergy facility here. You can see the little corner here. It's a brand new 160-foot secondary clarifier that kind of blocked us off. We get into some environmental areas just off the bottom of the screen. Then everything along the left side, these are all different equalization ponds, flow retention ponds for the facility. So kind of a hard boundary all around this left side and the top side of the facility. Coupling with that, this whole area was where they had all their old biosolids facilities prior to this. And they have a number of very large main drain lines that run through here, coming up down this road right through here. This is where their main filter backwash is returned back to the plant influent pump station, which is up here in the top part of this picture. So a lot of very major drain lines, and then obviously the there we go. And obviously we have all these challenges here on the left side with flow in and out of these retention ponds. So a lot of things we had to consider, and ultimately that was a big driver for how this was laid out and really some of the decisions we made during design. So talking about the digester, so we'd spent a lot of time in the design phase. This was progressive design build, so very collaborative through the design phase, working with the design build team, the program manager, the WSSC as the owner. How do we get the digester volume that we need? So we figured out what the digester volume we need is, but one of the things we had to contend with was this plant happens to be in the view shed for Mount Vernon. And so kind of what was established was on this site previously, there was an incinerator building. So that was, we were given that the top of the incinerator building was the highest point that we could have any structure. So we kind of had to fit within that. And then on top of that, we're also right next to the Potomac River. So we end up with some subsurface challenges. And so we only have so far deep we want to go without having to sink in our mixing pump stations and other things for the digesters. So we kind of gave ourselves a Starbucks menu of different digester sizes, looking at different, we kind of knew what our sidewall depth was, could be, and how much volume can we get out of it, but also realizing that the larger diameter we gave it, that ate up more of our site, and knowing that we have tight site constraints, that was a challenge as well too. Just to put it in perspective, so Mount Vernon here on the left side, so while it is technically in a direct line and is technically part of the Mount Vernon viewshed, I would find it, we actually had some folks go over to Mount Vernon in the fall after the leaves came down with a very high-powered camera, and we couldn't find the site across the river. But needless to say, we and the owner had committed to staying within that height limit. But just to put it in some context for everyone here. The other thing we needed to consider, and we'll talk about why in a minute, is rapid volume expansion. So for those who, I imagine that we have a number of people here who deal with digesters on a pretty frequent basis, so maybe you're familiar with this, but really looking at this rapid volume expansion. So what is it? It's basically when you get additional gas holdup inside your digester liquid material, and you can imagine that as that liquid space is taken up more and more with gas, that liquid still has to go somewhere, so it goes up. And then you end up in a condition where you have your digester, historically maybe it was called foaming, but this is really a different condition than a foaming situation where you're just getting this gas holdup that doesn't let the gas get out of the liquid matrix. You can see that during startup. You can see that during mixing challenges. You can see that when mixing changes its intensity, usually on the downside, if you're not getting good mixing, or if you have sudden swings in your digester conditions, they can all contribute to that gas getting held up in the sludge, and you can have some pretty interesting problems with that. So this isn't something that only happens in digesters. I am a big Coke Zero consumer. This is the old Coke Zero can. They didn't have a good picture of a new one, but same kind of idea is what happens when you get a shaken up soda can. So. But what does RVE look like, and why are we so concerned about it? So we'll go through just a handful of pictures. You can ask questions. I will not reveal where these are from to protect the innocent or otherwise, but we have some situations where we've seen some rapid volume expansion, and can make a pretty big mess pretty quick. This is one facility where it happened. This is a much worse outcome, I think, than the one we just saw. You can see it all running down the hillside here, and you see it all over the walls of this digester. Nice little sludge river going down the driveway down here. You get some hay bale berms and other things trying to contain it here before it gets to that roadway. So really not where you want to be. And so one of the things we were trying to do is how do we address the risk of that in a situation where you have a digester that is maybe a little taller than what some typical digesters might be, and also has the propensity for higher gas production. So those are two situations that can really cause additional risk of rapid volume expansion. So under some work that the program management team had done in conjunction with Bucknell University, they did quite a while worth of lab testing on the WSSC biosolids, and what they found was that they could see up to 30% volume expansion. And you can see here, so for those who know Matt Higgins, he's done rapid volume expansion testing on a number of different sludges for years and years. So for him to come out and say it's the highest values seen in the Bucknell laboratory, that means something. And so we as a design team were then kind of tasked with, okay, how do we deal with that? How do we deal with that expansion without causing a problem throughout the plant and making a big mess all over the ground? So that was kind of our task there. Sorry, do we have someone trying to ask a question? Can't tell. Okay.
I'll keep an eye on it for you, Matt.
All right, thank you. I appreciate it. So what did we do? So we did two different things. So one, we looked at how we're going to design our digester. So we got a couple of different zones here in this schematic digester. So don't take these to scale. I'm not that good of an artist. So we have that central portion there that's kind of our bulk active digestion volume. And what we were looking for was to get 95% or more of active volume in that digester. And so we know we're going to lose some. There's going to be some grit buildup. You can see that at the bottom. maybe a little bit of inefficiencies in the mixing system, so we don't get quite full mixing out of it. But what we did is we defined this active digester volume based on what we needed to achieve our SRT goals. And then that kind of set us with our normal water surface elevation. And so that's where, so these digesters have it's a standpipe top withdrawal type of configuration. But what we did, we actually put the top of our sidewall about 8 feet above that. And so that gave us, or our upper overflow about 8 feet above that normal surface. So if we had a rapid volume expansion event, we have 26% volume can be contained within the digester before you even come close to making a mess. So that was kind of the first piece here. That was kind of the first way that we got most of the way towards the rapid volume expansion containment. So 26 out of our 30%. So what did we do to get the other 4%? So this is again a 3D model of the digesters. You can see here we have our overflow connection here off the side that actually comes kind of standpipe style inside the digester, so it comes up higher through a inverted trap to contain the gas within the tank. And then you can also see at the top of the digesters, we have our emergency relief manway here at the top, built inside this little concrete 3-sided box. So the intent is that if we do get to an overflow condition, it would come out through the overflows, and then we have this channel system running alongside the digesters that'll collect it and contain it. And then at this end of the channel system, it connects into a plant drain manhole. So again, trying to keep it, even if it happens, which beyond 26% seems like an enormous number. But if we do get there, at least it's contained, it's controlled, and can get back into a drain system without becoming a big mess on the site. Similarly, if we continued to expand, we had to use the emergency relief manways. We have that connection here. This box is really designed to channel it down the wall into these channels as well. So, I see a couple questions popping up here.
Yes, and apparently you have your colleagues are helping you out here.
Thank you, Mike. Yeah, so
they were just asking what's the travel time from influence.
Yeah, so for some of these plants, for some of the farthest plants away, just in the truck, it's probably could be an hour to 2 hours depending on traffic. The DC Beltway is not your traffic friendly zone here. Yep, Janine was just there this week, so you experienced that fun. I don't know the exact travel time from the influent at the plant. I don't know. I think each plant's a little different with its size and its configuration, but even once the sludge is dewatered, it's a pretty substantial amount of time. I think some of where you're going with this, Kendall, may be in a context of how much gas production, is there kind of ancillary digestion and degradation happening before we get here? We'll come back to that question in a little bit. So this was our 3D model on the rapid volume expansion piece. And then just as we look at it from an aerial picture here, this is, kind of yellow is kind of what it looks like, kind of how it looks like in an actual picture. So again, our Revit designers did a wonderful job of portraying our designs, and PC and their construction team did an excellent job at putting this together to really, so we had a really good idea all along in what this looked like. But kind of that connection point here at this right side of the picture into the plant drain system, that's kind of the key to this whole process. We had looked at a number of options for how to do that. There's a lot of options that were very challenging to construct. This was one that was relatively easy to construct and still achieved our goals without being overly costly. All right, so this is one of my favorite parts of any project, is seeing how the construction goes. So it says photos, but we're actually going to start with a little video here. I think the audio may come through as well, but I'll try and kind of narrate over it. So PC hired a firm that came in and did. I don't know if you guys hear the music or.
No.
Okay, well, I hear the music, unfortunately. Okay, that was very loud in my headphones. Anyway, so this is just kind of this is back from August 2024. So kind of we are at the end of construction, so you can see this nice bright sunny day. Got all the different facilities. We get kind of a full 360 spin on it here. Obviously, we have our 2 large digesters here, each about 1.55 million gallons, so just over 3 million gallons total of digestion. Building adjacent to it that houses our mixing and recirculation and transfer pumping, as well as an electrical room. This side of the kind of in the front of us right now, this is the whole gas handling side of the house. And then as we get down here, just to the left of the digesters, we have our cake receiving, our cake silos, our thermal hydrolysis. The bigger building on the left was the screening, pre-dewatering, and post-dewatering. And we'll see some other pictures here too, and I can go show that again if people didn't get enough of that. But so a little bit of pictures. So we're talking about digesters. So we'll show the digesters. A couple of interesting things with the digesters. There's a lot of talk about access to the top. How do we do that in a cost-effective way? These are not short digesters. So we have kind of a main stairway coming up on this one digester, bridge that goes between the two, and then an emergency ladder coming down just to provide that second means of egress. We got platforms located periodically to meet the access needs there. The pipe rack we see here, that's taking the sludge, the digested sludge out of the digesters. There's a digested sludge storage tank just off to the right before it gets pumped from there over towards post-dewatering. Kind of flipping around to the other side of the digesters, this is our digester gas line here. We have a big condensate sediment trap here. Try and grab as much of the water as we can. And then if we continue to the right on this picture, that's where the gas handling and our engine generators and boilers are. All of the pipe racks over on this side, this is the digester feed coming from the thermal hydrolysis process, as well as the steams, as well as a backup steam supply coming over here in case for some emergency heating needs. And then this building right in front of us, that's our digester control building and pump building. Taking a look inside that building, these are the two big chopper pumps mixing one of the two digesters. Just you see the back end of there's two other pumps here just past them that you can't see. Those are the recirculation pumps. So recirculating from this point back, mixing with the thermally hydrolyzed sludge prior to cooling and then going back into the digester. And then kind of continuing along in the process, this is a picture of our post-dewatering facility here. So again, Janine mentioned before, thank you to BDP for sponsoring today. These are 4 of the 7 2-meter belt presses of theirs that we have on site here. This was taken obviously just before the belts were installed. But so this is the post-dewatering side. So this picks up the digested sludge, dewaters it. You can see the 2 incline conveyor trains coming out the backside, heading over to our cake storage facility. Which is here. So we have dual truck loading lanes. They can either load directly into trucks, as you can kind of see happening here, and then or it can continue in the conveyors and drop down into our underneath our big tent for on-site cake storage. You can see the product here a little bit. I didn't have a good picture of the product, but it's they're running about 22 to 24% depending on the day. And again, that's that's a Class A product. We're right at the end of commissioning, so we're still going through some of the testing to get all the certifications WSSC needs to have it officially registered as a Class A product, but that is where this is going. All right, I'm going to jump over into the kind of some commissioning parts of this. I think we're doing pretty good on time here. So I think some of the key things with commissioning is you really got to plan for success. And I talked about before, this is the startup of 2 independent but highly integrated biological populations. So we had and then each of them need their time to acclimate. Obviously, the side stream being an Animox process, they are very slow growing bacteria, but once they do grow, they perform quite well. But so we had a lot of steps in that side stream process to really make sure that was going to be up and running. So this was our plan. We spent a lot of time kind of trying to put this plan together, really, so we were prepared to go into the startup. And some of our favorite quotes kind of come out here. So, Mike Bullard, who's on the call here, this is this kind of came from you, and you're right. We made it through first contact. It was the second contact that kind of bit us a little bit. And we'll see a couple things here. But overall, the commissioning has been going on. We first seeded the digesters back in, I think it was May of 2024. So it's been just about 11 months now. So we've been running along for 11 months, and it's been going pretty well. Obviously a few bumps in the road here and there. So kind of we look at our model here. So the blue line, this is kind of how we had planned out what we were going to look like for how quickly we're going to grow volume in our digester from our initial seeding volume, water and seeding volume, and then also how quickly we can ramp up our feed rates to the digester. Need to make sure that we are not overloading the digester, providing it too much food as compared to the biological population's ability to handle it, but also we also need to be cognizant that we have a downstream biological process. So a lot of the digester ramp up in that orange line was really driven by the side stream's ability to accept the nutrient load from the filtrate that we take out of the digester. So a lot of things that we're trying to balance all together, which made for the spreadsheet we have that built this. Quite the spreadsheet, lot of columns, a lot of calculations. But the important thing, it's full of a ton of assumptions. And we're going to come back to that conversation here too. This was all done before any of these facilities ever seen a gallon of sludge going to it. So we had to make a lot of assumptions. That Bucknell testing we talked about provided a lot of inputs for it. But obviously we learned a lot over the last 11 months as well too. Talking about the side stream, there's a lot going on here, but really the key here is we had to be very careful with how we ramped up the influent nitrogen load to the side stream. The design build team had a performance guarantee with WSSC where you had to maintain a return load back to the liquid plant below a certain number of pounds per day. So we really had to make sure that whatever we fed to it, the process had capacity to remove enough of it for us to stay under our limits. So very careful adjustments of loads, working very closely with Veolia, the supplier of the Anitamox system is what we have here. So working very closely with them, building off of their knowledge from other facilities, really making sure that we had a solid plan for this. So that's kind of what we showed with our models. But the other quote that Mike loves to use all the time: all models are wrong, but some are useful. And I would say we proved that in about 100 different ways through this. So it was incredibly useful. But again, it's a model. It's designed to be wrong. If it wasn't wrong, it'd be real life. So always have a little bit of fun with our quotes here. So how did we do on the commissioning, and what did we learn? So I think the first thing we learned is that it's never going to go according to plan. So this was taken maybe 2 or 3 weeks ago as they opened up their pulper tank on the thermal hydrolysis process, and they had some issues with some of their extruder nozzles getting clogged. So this is, let's see if I can, so you can kind of get a little better view of what we had in here. So we pulled out obviously a fair amount of construction debris, some washers and things. We got some rocks. We have some metal chunks. This looks like at one point, one of the trucks delivering some sludge had lost a hinge. I think we found it. But all these things, just things that you wouldn't have thought of. We got a little coat hook here. It's not what I expected to see. And you got to remember that this is all the sludge that came in was previously screened. So hopefully a lot of this is construction debris, but there's a number of locations post screening where the sludge there's opportunities for other materials to get introduced in the truck loading dump bay, and some of the hoppers on the backside of the pre-dewatering belt presses. So lots of risk, and just need to be able to get at stuff and figure out how to deal with it. All right, so let's look at how well our model did for a second here. So the orange line was our model in terms of our digester volume, and kind of how we built that digester volume. So you can see I think we did pretty well with our digester volume prediction. What we find is that as we got out here farther in time, we needed to be very careful that we kept enough sludge coming out of the digester so we can continue to push and feed the side stream treatment. And so you see some of these dips like out here and towards the end of February, beginning of March, we had some challenges. We had some needs to take the thermal hydrolysis process down, but we needed to keep pushing side stream. So we kind of had to rob our digesters of sludge for a little while with the interest in keeping side stream moving. But then, as THP was able to come back online, we were able to push more through it and kind of make up for that deficit and get ourselves back up towards our target digester volumes. Talking about the total loading to the facility, so dry tons per day. So again, generally did okay. What we see kind of in that October-November timeframe where we didn't quite make where we thought we were going to be, that's where we started to see the impacts of the slow-growing Animox bacteria. So again, I could talk about side stream for another hour. We'll leave it for the point of here. If people have questions, we can talk about it. But the driver for this reduced load was really making sure that we could treat the filtrate and achieve our other goals. We have recovered. We see a lot of spikes here. Again, we had some some ups and downs from the thermal hydrolysis process and the boilers and needing to get those dialed in. So that kind of, as you look day to day, you kind of get that variability. But, since January, the end of January, we've kind of been steadily ramping back up. And we're at the moment, we're receiving sludge from all 5 facilities. So we've kind of gotten to that point of getting them off of their old hauling contracts and bringing it all here to Piscataway. All right, so we talked about the number of assumptions that were in the model that we originally built. So the orange line here is our original model. That was built on about a 45% VSR in the digester, which is pretty low for it's actually very low for a THP process, but we had some data that showed some potential inhibition of the digester based on some of the constituents in the sludge. That was a conservative. So we were looking at, when you originally modeled it, we were looking at a more conservative approach that would have basically had reduced gas production and more solids going downstream. So that's kind of how that was our safe approach. As we got into it, we were actually seeing that we're seeing closer to 60% volatile solids reduction. So that's the green line. So we kind of updated our model, but kept the original one so we can see what the differences were. And still not quite. And this is total solids in the digester. So maybe we're seeing a little bit less than what we thought we were going to. But in the last month or so, really gotten ourselves right up to about where we thought we should be in that 5 to 5.5 range for a THP digester. So things are looking, especially now, looking really good with where they're supposed to be. Even some of this, little bit of gap here, maybe we're half a point off from where we thought we were going to be, but not too much of a challenge or too much of an impact there. One of the big things with THP digesters is needing to maintain and track your ammonia concentrations, trying to keep it below the threshold where you might be toxic to the methanogens. Kind of in somewhere in that right around the 3,000 mark is where that risk starts to come into play. And so, again, our original model in the orange line, we thought it much less volatile solids reduction. We have less ammonia release from the cells, so we predicted a lower ammonia concentration. But as we saw our increased VSR, kind of had this additional ammonia release. So a lot of this was based on some data from the Bucknell testing in terms of what they saw for pounds of ammonia released per pound of volatile solids destroyed. So I'd say we're probably not releasing quite as much ammonia as they had in their original testing, but we're hovering right around that 3,000 milligram per liter in the digester. So staying in that, that upper but still safe range. And continue to manage that with how we dilute the sludge from the THP coming into the digester. So that's our knob we can turn to adjust and maintain that value at a safe number. The interesting thing we saw is that this purple line, so this is what we see in the filtrate. And so somewhere between the digester and the filtrate production, we're seeing a decrease in that ammonia concentration. And some of it may be the influence of the dilution water from the polymer. As we're adding more water to this, there'd be a little bit less concentration of ammonia. I don't know if it's quite enough to show me, for me to convince myself of a 33% reduction. So maybe there's some volatilization coming as it goes through the belts or into the filtrate collection system. But so our filtrate that we're producing is right around 2,000 milligrams per liter, and that's been pretty consistent for the last 6 months or so. Digester gas production. So this is much more frequent data than what we had in the other ones. So that's hence all the extra dots here. I'd say the key line to look at here is the purple. That's kind of the total gas off both digesters. So we are running, currently up around 650, 700 CFM on the gas production. So really even a little higher than what we had predicted. But again, as we talk about the number of assumptions that go into that, there's more than a few things that impact that in the model. So it's not too far off from where we would have predicted with the 60% VSR, a little higher though, but a little more gas is good. And we can continue to convert that to RNG and continue to sell that back to Washington Gas. All right, so we're just going to wrap up real quick here. I think I'm just about on time for where I wanted to be. So I think, models are great planning tools, but really nothing, doesn't replace real life and doesn't replace the need to have people paying attention, collecting good data, reporting the data, and working together to take what we found out today and how do we change things for tomorrow. That's really how we did it. We had a team on site. There's representatives from the design build team, both on the design and the construction side, as well as a whole bunch of support from the WSSC staff. on site helping, really paying attention to this day in, day out. And what we found is that small changes are important. You know, little change can make a big impact real quick. And like I started out, it's all about the people. This is a picture from right after the first truck of seed sludge came in from DC Water. Done at, I think the earliest they were allowed to show up was 1 a.m, trying to avoid traffic between Blue Plains and this facility. So it was all done overnight. So you can see the very dark photo here, and a bunch of very excited folks to keep things moving here. So definitely a big team effort. Can't say enough about the support we've had from WSSC, from PC, from Stantec, and the program management team. So yeah, I've had a lot of fun with this project over the last 8 years, and it's really pretty neat for me to see it fully built and operating pretty much where we want it to be. So I think maybe about 4 minutes short of what you said, Janine. So I'm pretty close. So we got a bunch of time for questions, and I'm ready to go.
Yeah, all right. There's one lined up there, but thanks. I'm glad that you like to have fun. I would like to work on a project with you, Matt. That sounds fun.
No, it's, if we're not having fun, then it's a problem. So that's okay though.
Yeah,
Let's see.
Work seriously, but not yourself.
Yeah, you gotta have fun. Let's see. So Al, good question. How many days of on-site storage available for Class A dewatered material? Somewhere around 7 days right now. So at the design, so let me rephrase that. It's about 7 days at the max month production rate. So at like full throughput of the plant, about 7 days worth of storage. That cake storage tent has the capabilities to be doubled. There's space next to it to do a future expansion to that to provide up to 14 days there under the tents. That was as we get into the everyone, this was constructed designed right before COVID. I think they started construction about 2 months before COVID hit and shut everything down. So there are a bunch of impacts to the project based on cost challenges, material shortages. So there's definitely some value engineering and some phasing that got looked at, and how do we best allocate money from WSSC to get done what they need to get done right away.
All right. Al says thanks for that answer. Yeah, maybe we should have another webinar on the side stream processes, because yeah, I could geek out on that.
Yeah, no, it's interesting, and we definitely, well, that'll have to wait a little bit. We're not quite, actually, let's see. Today is day 5 of their performance testing, so we got another 25 days to go before we fully check them off. So we have to wait a little bit till everyone gets themselves contractually set up here. Let's see, what is the daily average SRT in the digester? So I think currently we are probably running in the 25-ish day range, 20 to 25-ish day range. I think, again, we're running at about, I don't know, maybe 75% of full load capacity. So I guess we're probably closer to 20, actually. I don't have the data right in front of me, Timothy, but I think the design load for the digester looked at no less than about a 12.5 day SRT at full THP throughput. So the THP throughput max is about 92 dry tons per day. Digester size at that peak flow for 12.5 days.
You guys can just take yourself off mute at this point if you want to ask questions directly, but yeah, I've been through a few construction projects in the past, and they never go as planned. But it seemed like you had some really bizarre challenges. Well, I mean, being between a rock and a wetland, that's pretty typical at these treatment facilities to work around. But the view shed of Mount Vernon?
Yeah, it was the WSSC, I think, has had challenges in the past, not recent past, but I think, like I said, this plant originally had an incinerator building, and they built that as tall as they were allowed to. Funny story, the incinerator ran for, I think, through performance testing and then was pretty much immediately shut down. This was probably bad. I'm not sure exactly when it was, 70s or 80s. The story, and don't know if it's fully true or not, was that one of the neighbors was a local judge, and he didn't like the incinerator, and so he helped to shut that down. So,
Matt, this is Tim again. Let me ask you a follow-up. Going back to your slide on the solids the dry tons in and out. If I caught it right, from what was not converted into biogas, you had 69 dry tons going in, or 68.3, and then 24 or a 42.2 as dewater Class A solids. So that's like about a 39% total solids reduction. Does that line up kind of with then the 60% VSR? I guess I would have thought that the total solids reduction
It'll be
of
less.
THP solids would be more.
It is. So again, this goes back to these numbers were produced prior to. I probably should update them. That's a good point, Timothy. This is based on the original assumptions, based on a low VSR value. We were looking at like 45%.
Oh, okay, that was on
So,
the 45% VSR.
yeah, these are. This is back from the design level mass balance.
Yeah.
So it was not updated for observed
Right.
conditions through startup.
Right. So you figure you're getting probably greater than 50%, 55, or
On-
50s on the 60% VSR of actual. If
We're
you
getting about 60% VSR. I'd have to go back and back calculate the TSR, but it's about 60% VSR. So yeah, I would say it's. I mean, if it's 68 in, it's definitely less than 42 out.
Yeah.
Yeah.
Okay. Fair enough. Thank you.
You're welcome.
Matthew, Chad Whiting from MWRA. Excellent presentation.
Yes. Thank you.
Just curious on any of your challenges to clean up the gas to pipeline conditions to be able to sell it back. Can you talk a little bit about that?
I can talk a little bit. Yeah, sure. So the gas cleanups, I don't have any slides on it, but the gas cleanup system is a water scrubber based system. So it has iron media, it has carbon media, and then has the iron media to remove hydrogen sulfide, the carbon media to remove some siloxanes and other materials, and then the water scrubber system to remove do the final removal of the CO2 to clean it up. So that system, I would say I wasn't that was part of this project that Stantec was directly involved in, so I can't they would have more details than I can. I can get your information and get you connected with someone who can answer some more specific questions, but currently it's treating gas. It's treating gas to pipeline quality. They're still gathering enough data to prove to Washington Gas that it's consistent as they need it to be. I think that's probably the biggest thing that we've seen is not so much the performance, just Washington Gas's concern with consistency and reliability. I think the treatment process relatively proven. We know what it's going to do. Just Washington Gas being the manager of this distribution system, very particular about blips and avoiding those. I mean, one of the big things they're concerned with is oxygen. In that we don't foresee that to be a big issue, but definitely something that they have an online mass spectrometer that's mounted there at the gas treatment systems process. So they're doing real time mass spec analysis of the gas to get the constituents to feed back to Washington Gas and prove it's what it needs to be to meet their criteria. From what I understand, the instrumentation side of it is the part that I don't think probably haven't run into too many issues with it yet, just because it hasn't been running that long yet. But I think that's the part where there's the biggest questions and maybe the biggest importance as it relates to the ability of actually exporting it to Washington Gas.
Thank you.
So Matt, Romy's asking the question we all want to know: where's the dewatered cake end up?
It's going to continue. The plan is to continue with land in the near term. Continue with land application. Most of what WSSC produces is land applied in Virginia. So, which is where a lot of the if you going back in history, it's where a lot of Blue Plains and a lot of Maryland facilities send their biosolids to Virginia for land application. WSSC is looking at, when we were separate from this project, we were involved in some longer term planning for them, looking at opportunities to take this Class A cake, transform it to other products, looking at future regulatory drivers. How many presentations have people gone to recently where those nasty 4 letters haven't been mentioned once? And I'm not going to break that streak. So we are, so they're looking at future regulatory drivers, future constraints on hauling costs, looking at drying, look at other opportunities to continue to be efficient. And one of the things they're really interested in is continued improvements to the product to open up new markets for the biosolids, whether it be into like a fertilizer blender, a soil blender, just other ways so they're not fully reliant on not fully reliant on land application with some of the risks that may be looming out there.
Yeah, smart.
Hey, thanks. Hey, Janine. Thanks, Matt. Great presentation. I was curious about the mass balance on the ammonia that you were talking about. I think you were saying, if I understood it correctly, you had hovering around 3,000 milligrams per liter in the digester, but only 2,000 in the filtrate.
Yeah, correct.
Roughly. Have you done a mass balance on that to see where the 1,000 milligrams per liter converted to pounds is existing? I mean, it's not going out in all the biosolids, is it? I mean, am I missing something here?
There's probably some that's in the biosolids. I mean, right? Because there's some that goes with the biosolids. I think there's that 1,000 milligram per liter gap is probably some combination of some in the biosolids, some dilution from the polymer and the extra water that comes as carrier water with the polymer, and then I would imagine that there is some stripping that happens just through the cascades. It is cascades in the belt press.
Yeah, I was wondering if there was some off gassing of it too.
I mean, if you've been in, I mean, I imagine many of us have been in dewatering facilities. You're gonna smell like ammonia when you walk out, right? I mean, that's so it's definitely in the air. So there has to be some off gassing, whether that's straight from the sludge or from the filtrate cascade. Not really sure, but have we done enough testing to directly attribute, how much of that 1,000 goes to each spot? No, we haven't.
Well, I guess it's a good thing because you've lost a third of it, before you have to go to your side stream treatment, right? So,
well, what's funny, normally you would think that, but when you're trying to do a performance test on a full load to a dual reactor system where you're starting up at maybe you're at a total of 60% of your load or 75% of your load to the system, I could use a few more pounds of ammonia right now.
Exactly.
Yeah.
Thanks.
Yeah, absolutely. We'll be sharing the recording of this early next week for all of you. I did have another question. On the design for the digesters, were those stationary covers? Or
yep,
floating?
those are fixed covers. So the digesters are done by DN tanks. So let's see, go back to this picture. That's a decent one of the covers. So yeah, done by DN tanks. So it's all concrete, precast post tensioned with a cast in place concrete cover, fixed.
Awesome. We had a presentation maybe a couple netters ago about Columbus, Ohio's leak detection, their findings with the floating covers. So keeping the gas. All right.
Keeping the gas inside is important. Yes, that's the whole point.
All right. I think those are all the questions, unless anyone else has burning one.
Matt Haven, APA, CDM.
Hey, Ben, how you doing?
Good.
Good.
Awesome presentation and project. I've been following you for the last, like you said, many years on this. One thing I thought I heard you say was somewhere around 22 to 24% total solids off dewatering.
That's correct.
Any lessons learned? I think we're all seeing some more data points on polymer dose, on importance of polymer mixing. Some are diluting the sludge post-digestion. Some are doing dew point, chemical addition. Any thoughts on the lower bar on cake solids or lessons learned in general? And it sounds like you got a lot of variability in sludge too.
Yeah, we have a lot of variability. And so one of the challenges we have is maybe only over the last 4 to 6 weeks have we had all of the plants here come bring their sludge here. So literally this week, we're just starting to see some challenges with dewatering as all that sludge has, kind of worked its way through the system and kind of become digested sludge now. We do have dilution between the digesters and the post-dewatering belt press, mostly to facilitate polymer mixing. We have multiple opportunities for polymer injection. We also have both a motorized inline mixer as well as your traditional variable orifice weighted polymer mixing valve. So multiple places to inject it, multiple ways to mix it. We do use the dilution. They have been using the dilution water going into the presses. They get a little better. It's not so much the polymer mixing, I think, that it helps. It's more the distribution of the sludge across the belt at slightly lower concentrations. So they're still playing with it. I guess the short, and now that they're seeing what the full combined sludge is going to look like getting onto the belt, we're kind of revisiting some polymer thinking and trying to figure out, how do we optimize that? Is there potential to go higher? I think so. Have we fully dialed it in yet? No, not yet. We do also have between the digested sludge storage tank and the post dewatering belt presses, we also have a small ferric system, so we can add a little bit of ferric primarily for potential struvite control, as some of the WSSC plants are converting more to biological phosphorus removal and more away from chemical. So we do expect to see some increased risk of struvite. How much we'll see, we don't know yet. It's not all the plants, it's not all the biggest plants. So it's a little bit unknown exactly what that looks like, but we do have the ferric system there primarily as defense against struvite. But we do expect that the ferric will help a little bit in the dewatering performance as well.
Sounds like you have a lot of levers to pull if and when needed.
We do, which I think can be. I don't know if we have. I probably don't have any of the. I think some of the operators like it, but I think it's a lot for them to try and wrap their head around too, right? I mean, yeah, just giving a lot of options, and with the options, and we've done a lot of work developing SOPs and some other operating guidance for them to try and help give them some direction as to how to work with the different knobs and levers.
Yep. Thank you.
Yeah, great work, Matt and team.
I see a hand raised.
Right.
Matthew Fraser.
Yes, first, thank you for the presentation, much appreciated. Second, I'm not sure if it's a discontinued arm of stormwater agencies anymore, but for a while it was the Water Pollution Control Division. Do you ever work with agents or ambassadors from stormwater that collaborate with your team on any specific projects?
Is that a combined system, Matt?
No, the WSSC isn't a combined system. I guess, Matthew, I'm not sure exactly. I don't know. Maybe I'm not quite understanding what the question is here.
For the effluent side, if you ever work with stormwater inspectors, or everything is done entirely in-house with your own inspectors and regulators internally?
So I think for a lot of the effluent side of the plant, the liquid side, that's more WSSC than us. I mean, they manage their own permits and they're in charge of compliance there. We do have a stormwater. We do have a number of stormwater management features on this site that we had to put in. So we did have a lot of interaction with the regulators and with making sure we had the right stormwater controls. But I'd say a lot more of the day-to-day management and coordination on those permits and those requirements would go through WSSC, not so much the design build team.
Thank you.
Hi,
Yes.
Janine, I'm back on. I know you got
Hey,
2 minutes,
good.
2
Why
minutes
not?
left. And this is no disrespect to the program sponsor, BDP. I noticed you use belt filter presses for dewatering. Is there a reason you use belt filter presses versus other technologies for dewatering? I'm just curious because we do a lot with other technologies, not so much with belt filter presses these days, but we're not doing digested solids either. They're raw biosolids.
I'd say certainly there's cases for all types of dewatering technologies, depending on things. I think the biggest driver here was a very clear client preference to stay with belt filter presses.
Yeah, we've seen that before with certain clients that we have a preference for that technology, and again, we've worked with BDP before, great company, so no concerns there. I was just curious the reason for the choice, or if there was an evaluation of different dewatering technologies. But thank you.
Yeah, that choice was pretty prescribed from the beginning.
Fair enough. All right. Well, I'm going to go ahead and get this wrapped up by thanking Matt so much for your time in doing this presentation for us. I want to thank BDP Industries for sponsoring today. And thanks to all of you for joining us. If you have some suggestions, I'm continuing to line these quarterly meetings up for the next year and a half or so. So email me if you have a suggestion. Happy to follow through on that. So thanks again, everyone. Have a great weekend.
Thanks, Matt. Thanks, Janine.
Thank you.
All right. See ya.
Thanks, everyone.